All right, so we're going to pick up where we left off last time, and I'm going to try to wrap up the kind of this machine learning part in the first hour, and then in the second hour, we're going to, sorry, my pets are destroying things over here. It's okay, it's just a little distracting. Anyway, we're going to look at we're kind of going to invent a technical interview, basically. And we'll probably take about 45 minutes at the end to do that. So apologies for all the scraping and sounds and things of animals running around. Okay. So last time, we imported this data, this iris data. As I said, this is a toy data set, very common, and we're just really using it to proof, to really demonstrate a simple model, KNN, that I kind of walked us through last time. So we've got these four features: sepal length, sepal width, petal length, and petal width. And from those features, we're going to try to predict the class of the iris. Okay. So I read in that text, that set of data, into a data frame, a pandas data frame. That's the data structure in pandas. And even though I didn't need to do this, I could have just said columns gets names up here, but I did columns gets df.columns just to show you that there's this field for each data frame that is the columns of that data frame. And I think that's, if you're going to play around with pandas, it's just good to get that light familiarity to start off with. So here we're looking at the first 10 rows of data. If I wanted to see the last 10 rows, I could do this, df.tail, and that's going to get me the last 10 rows. Let's see, do I need to? No, everything's good. Okay. All right. But I'm going to leave that as head. It's not a problem to have that. And let's just get into some more ways of, light analysis. If we're just peeking at a data frame and trying to figure out something about it. So what if we want to know what all the class names are, that are in our data? We can access the class names like this, df subclass. And notice this is going to give us this thing. It's kind of like a list, right? It has an index that's explicitly stated, and it has a value. And if I look at the type of this, we can see this is a pandas core series. It's a series. So a series is just what we think of as a column in a pandas data frame. Or that's a simple way to think about it for now, and that's how we'll treat it in this lesson. If we want to see all the unique values here, there's a unique method. And that's really nice, right? We can see iris setosa, iris versicolor, iris virginica. So we've got 3 classes. If we want to know how many items, how many rows are in this data, we can look at the length, just as we've always done. And we can see that there's 150 rows. Another thing we can do, although this is not entirely advisable, there are better ways to do this, but I want to show you kind of the wrong and easy way to iterate over a data frame. And maybe I'll do something like this, so we don't iterate over the entire data frame. I'm just going to show the first 10 rows. So for row in df, and let's look at the first 10 sepal widths. And let's say print row. We can then decrement this break at, right, by 1, and if that break at is less than or equal to 0, then we break. So we should get a printout of 10 items right here. So when you start learning pandas, there's this whole world of pandas methods, and they may not work as intuitively as you might expect. One of the real powers of pandas is that it's much more performant than iterating through a list of data. Okay, and you do want to use, fairly well structured queries. You want to use fairly well structured, or you want to use the methods that pandas provides. But if you have to, you can sort of treat pandas a lot like you can treat pandas a lot like just a list. And that's very convenient. So if we want to see the whole row, well, why are we only getting that? For row in df, print row, sepal length, sepal width, petal width, class. It turns out that that's not giving us what we'd expect. And it might make more sense if we're trying to, right, this is just giving us the columns. If we actually want to see all of those, we need to do something like this. Right. And oh, yeah. Interesting. I might be misthinking this a little bit. Row in df. Oh. Wonder if I accidentally. Oh my gosh! Sorry, my cat and my dog are fighting, and okay. Apologies for the chaos. It's a little distracting to me. I might have to do something about this in a second. At any rate, we can iterate through a data frame, and that's really the point I'm trying to make. We can treat it like any other data structure in Python. Not exactly the same, but we can do very similar things with it. So the place I'm going to start in this kind of EDA, or where I'm going to continue in this EDA, right? We got some basic ideas here, such as, what do our data values look like? What's the length of the data frame? What are the unique classes? We could, ask other questions like what's the range of these values and things like that. We could take some time to do that, but I'm going to go ahead and move forward because we don't have that much time. And I'm just going to plot our data. And this is a super important part of the exploration of your data. It's to get some kind of visual sense of what's going on. So I'm going to get I'm going to grab these from up here. And notice that I'm calling this X, and we often think about X as being the input to a model, and we often think about Y as being the thing we're trying to predict. Okay, so what I'm going to put in here is just the class from df. So notice what I'm doing here is I am kind of creating these subsets. I'm kind of trimming off parts of that original data frame into X and Y. And this is kind of cool because it doesn't actually make a new object in and of itself. It makes a reference object, and so you're not using memory. You're not double using memory necessarily here. You're kind of not filtering, but leaving out the display of class in X. So if I look at X, right, it's just it's just all the values except for the class. And if I look at Y, notice it's just the class. Both of those are still data frames. So that's the first thing I'm doing. I'm just kind of separating them out, and we'll do that again. We'll do that a second time later. And I'm going to build a plotting function, and to help me with that, I'm going to use something called a label encoder. This is just to help me to essentially take these values in Y that are currently, these text values, and give them a numeric equivalent. Sorry. All right. So I'm going to make something called plot features. And what I'm going to do with plot features is I am going to compare every combination of our features, right? So how many combinations of features do we have? Well, 4 choose 2 in this case, right? I am going to only look at these 2 features, and part of the reason I want to do that, let me open sketch document. The main reason I want to do that is I want to look for separability. And let's say I've got this plot, and I've got a bunch of, this is maybe iris versicolor, and then maybe this, let's find a more distinct color. And then, this is iris virginica. This would be kind of nice because I can see right here that there's some sort of easy linear thing I could draw between these two, and that would be nice. I can just sort of separate these out. Of course, we're going to be using KNN, so the linear aspect doesn't really matter so much. But even in this, if this is what our data looked like, it would be easy to classify. There's an issue with this in this data set. Most of the features will lead us to guessing the class perfectly through the KNN model. And these are highly predictive features of the class. So what I'm actually going to do is compare all of these, every pair of features against each other and look for the least separable 2. And this is not what you would do in practice. In practice, if you had such nicely separable features, you might even drop features that you don't need in order to make the prediction to make the whole process simpler and say, well, I could just predict, the class based on sepal width and sepal length, and that'd be fine. I don't need petal length and petal width. But in this case, because our model will likely perform perfectly almost every time, I'm going to choose the 2 worst performant features. And I'm just doing that for kind of pedagogical purposes. In everyday use, you wouldn't do that, just to be clear. You look for the best sets of features out of your data and drop features that you don't need. So with that, we're actually going to, first I'm going to call this label encoder. And then we're going to see a simple application of combinations. So in this case, I'm just transforming our Y values into numeric values, like numeric classes for easier, so it'll be easier to plot. So let's say for every pair of features, and I'm going to build this in a very procedural way. We could probably, we could call out to a library and get all these combinations, and that's what we would likely do in practice. But in this case, I'm going to do this in a very procedural way just to show that it is combinations. So for each column in our columns, and let's see, let's start from, I'm going to exclude the last column, and then for column 2 in columns, And from here, I can say if column 1 isn't equal to column 2, right? Because we don't need to compare sepal width to sepal width. Those are, you know, they're just going to plot to the same point. There's nothing that we're going to get out of that. So if that's, if column 1 doesn't equal column 2, and I am going to construct tuples, and column 1, column 2 as a tuple, if that's not in the built pairs, and if column 2, column 1 is not in the built pairs. So I'm just kind of accounting for both possibilities here. Then I'm going to construct a tuple that is column 1, column 2, and I'm going to attach that to our built pairs. So built pairs.append tuple, and why don't we just print the built pairs to make sure that that is doing what we want it to do. So I'll call plot features, and let's see. And then missing two required positional arguments, of course, we want to pass in x and y. And, oh, good, okay. Please change the shape of y to number of samples. Interesting. Okay, well, let's see if that bothers us later. Oh, you know what I didn't do? I didn't suppress warnings. So let me go ahead and do that. This is something that you'll find yourself doing from time to time, because you will get warnings in your code. So I want to just do that really fast. So import warnings, warnings dot filter warnings, and then we'll just ignore them. Okay. Again, the reason I'm doing that is the code that we're going to write is a little bit messy in a way. Like in production, we would write this a little bit differently, sometimes very differently, but the ideas are all going to be the same ideas. So I want to give you the kind of, when you trace through this, I want you to be able to understand it through a lens of base Python, at least most of it. So we've got these pairs, sepal length, sepal width, sepal length, pedal length, sepal length, pedal width, sepal width, pedal length, sepal width, pedal width, pedal length, pedal width. So we're going to make a plot for each of those. So for each pair in those built pairs, I'm going to set the label, the X label, as the initial part of the pair, the first item in that tuple. And then the Y label is going to be the second item, pair sub 1. And then I'm going to make a copy of the XDF up there, the X data frame that I have defined as a parameter here. So that's essentially our data, and Y is our target, just to remind you. And with this, I'm going to limit this to just that X label and Y label, and I'm going to get out of this the values. And values here is going to give me, it's just going to give me those values, right? We're sort of discarding the data structure of the pandas data frame when we do that. So after I do that, I'm just going to do a quick calculation for the min and max of both X and Y. And this, the way I'm going to do this is with this min method. And then I'm going to take 0.5 off of that, which is around the scale that'll give us some padding on the left and padding on the right. And then the max value is going to be X, and we'll do just the max of that same thing plus 0.5. And the Y min and Y max are going to be very similar, right? Y min, Y max, just to be clear here, this is x and y axis on the plot. This isn't y as the target variable. Okay, just to be very clear about that. Like the y I'm referring to here is the y that we're seeing there, right? Where this is x, this is y. So, okay. Now, I need to modify this a little bit. So this is going to be I'm putting 1 there because that's corresponding to the values that are in the y label, right? 0 is the x label. Okay, so we have that, and I believe that's good. So now we're going to build the plot. And the way that the first thing I'm going to do is I'm going to make this structure called a figure, and I'm going to set a size for this figure. And let's see. Then I'm going to plot a scatter plot as I did before. So plt.scatter. This is a really nice one to just kind of know offhand. Just plt.scatter, and I'm going to scatter those two features against each other. And that's how I'm accessing them here. I'm going to set a color, and I'm actually going to set a color map here, which is, you don't need to know really about this beyond, this is just going to automatically assign colors as we see them. And then I'm going to put I'm going to put an edge color around each of the plotted points. So that's most of our plot right there. And then I can just label the axes. So I'm going to label those with the names of those features. PLT X label, PLT Y label. And this doesn't really matter, but I don't want to see the tick marks. So I'm just going to get rid of those. They're not actually helpful in this plot, and they're there by default, so I'm going to get rid of them. And then we're going to pass in X and Y, and I'm going to pass in the columns. Is that how I define that? Yeah, I need to put a third. So this columns, where this is going to come from in my function call down here, it's from up here, where I grabbed the column names out of df.columns. So with that, let's see if that plots. PLT is not defined. That's because I did not import matplotlib, which originally I did right there. Okay. So let's try that again. And we get a bunch of plots. So we're going to get 6 of these. And remember what I was saying about separability. Let's just compare 2 of these, and we'll get a better sense of what I meant by that. So this is sepal width and sepal length. And then we've got petal length and sepal length. And this is just to get kind of a quick view as to how easy it should be to predict classes. And the further things are away from each other, especially in this two-dimensional space, the easier it's going to be to distinguish them from each other. And if we look at these side by side, I mean, these colors aren't entirely clear. We've got red down here, orange here, and gray up here. But, I can look at this and kind of draw a line through it. And I think that's indicative of it being fairly easy to make predictions on. And it's not that we're always going to get it right, but with KNN, in this combination right here, KNN on this combination will probably get to 100% accuracy, because this is a simple data set. And so let's not use this one. And if we were to scan through all the rest of these, maybe I'll just do that really quick. I'll set aside this sepal width and sepal length because it looks a little messier. But if we scan through the rest of these all look fairly separable, especially this red labeled flower here. So that first one that plotted, sepal width versus sepal length, is probably the messiest of them all, right? Like if I'm just thinking about this in terms of taking votes from nearest neighbors, if we've got 3 nearest neighbors, well, we're going to misclassify that one. We're going to misclassify that one. Let's see. We're going to misclassify, that one for sure. That one. We're going to get a lot wrong, right? And that's fine. That's actually what we want to do because we want to imagine as if we have a more difficult problem than we actually do. And we're going to try to solve this with the least friendly features, even though, again, in practice, we would probably choose the best features. It's just that won't be as interesting here. So the second part of this is going to be our train test split, and maybe I'll mark this as 2, train test split. And this again, just to remind you what this means, is like we've got this body of data, right? And we take, in this case, I think we'll probably do 80% and 20%. This is our train, and this is our test. And what we do is we take this and we put this into a model, right? We put this into our model. And this puts out a trained model that is capable of doing predictions, performing predictions, right? So now we can take this test set and make predictions on that test set. We can actually make predictions on the trained set as well. But quick question, this trained model right here, do you think it's going to make better predictions on the trained set or on the test set? Which do you think it'll have an easier time making predictions on? Yeah. So the trained set, right? Because it's been trained on the trained set. And so we can say it's familiar. It's a little anthropomorphic to say that, but it's more familiar with this data in the trained set. And it's not familiar with the data in the test set. The test set is there to, to mimic unseen data. So this is our untrained algorithm that we're training. This is our trained algorithm that we use to make predictions. So with that, I'm just going to, excuse me, I'm going to do this in the simplest way possible. Well, maybe there's a simpler way, but we're going to need NumPy. NumPy, again, is our I like to think of it as our linear algebra set of data structures, or really it's just an array, but NumPy is it's what is underneath pandas. Pandas can handle a bunch of different data types. NumPy tends to handle one data type. And then I'm going to say from sklearn, which do we have time for a quick aside? Yeah, let's just take a very quick aside, and let me pull up sklearn. So sklearn. so what sklearn is it's a machine learning library. It tends to be pretty academic. Academic in the sense of maybe it's not going to be as performant as some other models, some other tools that are out there, but all of our base algorithms are here. And this has this split into three categories: classification, regression, and clustering. We can think about classification and regression as supervised learning, and clustering tends to be unsupervised learning. Dimensionality reduction tends to be unsupervised learning. And then there's things like cross-validation kinds of things under model selection, pre-processing, if we're going to invent new features from the features we have, things like that. We could, let's see, I think maybe I did show this, sklearn supervised learning. If you want to kind of get have a quick read through of all the supervised learning models that are in this library, they're kind of all here, right? You can click on any one of these, like say logistic regression, which is a really good one to know. Logistic regression is a good one to know coming into the DSI. This will give you a short but sweet article on what that is, summaries of different aspects of this model that can be analyzed. Cool thing about this is, sorry, I'm going to paste this in. The cool thing about being able to look this up here is you get some text on it. You can definitely go to Wikipedia and read more. You can go to Archive and read about logistic regression. You can find logistic regression tutorials everywhere. But one of the things that's really great about scikit-learn is, let's say sklearn GitHub logistic regression. And here is the code base for the actual logistic regression. And, this is in a class format. Well, more or less. These have some helper functions, and there's a link. Let's see. There's a link to some other documentation about how it solves the problem of logistic regression, and loss functions, gradient approaches, multinomial loss, this is a fairly extensive file, but somewhere in here there is going to be an actual logistic regression function. Let's see. Is this a linear model? I think it'll just be logistic regression. There we go. There's the class. So here's our logistic regression class, and this has pretty extensive documentation, even in the code. They kind of over-document their code, which I appreciate, because you can go here and you can read about the model, and you can try to code it. You can try to code the model not from scratch, but based on what they've got here. Maybe a simpler version of it, and yeah, this is all class-based, and when you write models in the DSI, that'll actually be class-based as well. I wouldn't expect you to be able to go through this and really understand it now, but just know that there's this massive code base out there that you can just go to. You can go to and read through, and that's, I think, incredibly helpful. Okay, so sklearn is we use it a lot, especially in studying and learning about machine learning. So from model selection, I'm going to import this train test split function from sklearn.metrics. I'm going to import an accuracy score, right? We have to optimize for something, and I'm going to just optimize for accuracy, which is number of correct out of number of guesses. So from I'm going to import from sklearn neighbors the k nearest neighbors classifier, right? That's a classifier. It's going to guess a class after it's trained. I'm also going to import, I'm just going to import linear logistic regression here, but I'm not going to actually implement it. I'm going to leave it in this notebook in case you want to grab the notebook and try to get logistic regression to work and see how that performs. You'll have to change a few things around, but it's fairly plug and play, and I think that's one really nice thing about sklearn, well, approaching learning sklearn, is that you can try different models before you really even know what they do. So I'm importing all those. Oh, wait a minute. sklearn linear model, import oh, that's why. It's a class. You don't use camel case for a class. All right. Okay, so we know what our least separable features are. So I'm just going to build a new x. So I'm going to build a new x as this time a numpy array, because that's what I'm going to pass into this k neighbors classifier. And I'm going to give it the sepal, it was sepal length and sepal width as the least performant features, or least separable at least. And then I'm just going to get y out of this again. Although I already have it above, I could just cast that to a numpy array, the y I already have. But I like having this be a little bit explicit, because one of the things that you can consider is that what if you feed into a model the sepal length, sepal width, petal length, and the class, and you are trying to guess the petal width, right? You can change your target, and that's the kind of thing you might do. You really might do that. Which is it more important to be able to predict based on given data? Usually the thing that you need to know, right? Like the potential for a stock to drop in price tomorrow, something like that. That's usually what you might predict. But there are times where you'll have a lot of, say, features, descriptors of a human, and maybe your data set has as a tagged output, a y value, had percentage likelihood of developing a certain disease. Well, maybe if you already have all of those materials, maybe you want to predict on something else, right? That's in that data. So a feature can easily become the target that you're trying to predict. So I'm just putting this in there explicitly like that if you want to play around with that. So I'm going to split this into train and test. And this is going to be xtrain, and this is often the actual semantics of this, what we name these: xtrain, xtest, ytrain, and ytest. And I can just call train test split on x, y, and I'm going to say the test size is 0.2, which means that I'm doing an 80-20 split. And then I'm going to set a random state. The results of this are going to be wildly different based on the random state. And I'm just saying that up front because we could, and we should, if we want to be thorough about this, test a bunch of different random states and see how they perform. Or maybe we run this train test split without setting a random state, but we run it a bunch of times and then make a decision about our hyperparameters based on what we see. So now, speaking of hyperparameters, and remember, hyperparameters are just the things we're trying to tune in the model so the model performs better. In this case, we're going to search for the number of neighbors that get to take a vote. That's going to be the only hyperparameter we really consider here. So we're going to search for hyperparameters. And this is where we do cross-validation, this thing that I've been talking about. This is where we actually perform the measurements in cross-validation. So for k in neighbors, I'm going to build a k and n. So notice for k in neighbors, well, I'm going to have to build what neighbors, how many neighbors we're going to consider here. K and n is going to get our k neighbors classifier with the number of neighbors equal to k, and so how do we how many neighbors do we want to test? Well, we could we have 100 rows of data. No, sorry, 150. So it might even make sense to go up to 150 neighbors. But what happens if we have 150 neighbors and we're taking the majority vote, right? What happens? We just get, for every item, we get the majority class. We're going to predict all of one class. So it probably doesn't make sense to do that. I'm going to go ahead and say the number of neighbors that we consider is going to be in the range from 1 to 100. And I'm just going to make that a list really quick. So that's going to test 1 through 99 neighbors. And then I'm going to make once we have that model built and taught, right? Once we teach it through the data that's there, then we can make predictions. And the main thing we want to find out is the predictions on the test set. The cross-val test scores is going to be most important, but we usually also check how it predicts on our training data as well. And there are reasons we do that, which I'll touch on, but I probably won't go too deep into. It's nice sometimes to have as a foil, to have as a good comparison, right, to the test scores. So we have the trained scores, we have the test scores, and we really care about the test scores, but the trained scores are there to see how well the model is doing on the training data, and then we can kind of relate those and talk about that performance a little bit. So we fit the model, and all that means is we train the model using the data. So knn.fit, and we pass in xtrain and ytrain, and we get predictions on train. So let's say ytrain predict is going to be knn, and here we have just a predict method. So knn.predict, and we're going to predict on xtrain. And then we're going to from those predictions look at the accuracy score. So how do we get the accuracy score? Well, there's this function called accuracy score that we imported, and we compare ytrain, which is the actual values, the actual y values, the classes that we're trying to predict, and we compare that to the predicted classes. So what that's going to look like is however many we get right over however many we predicted, right? So this is just a simple difference. It's going to be ytrain minus ytrain predict, essentially. And so I'm going to append this to CV train scores. And then that's our predictions on the training set. And now let's get predictions on the test set. So this is easy to change. I'm just going to go, let's see. I can, oh wow, I can't actually do that in this space. You know how you can do Command D or Control D and have it expand the selection range? I don't know if Clark ever showed you all that. Anyway, I'll just change these one by one. So I'm going to pass in xtest, and I'm going to append this to CV test scores, and we're looking at ytest versus ytest predict. So that's, why is k neighbors classifier is not defined? Oh, that's because it's k capital N neighbors classifier. Okay. And, oh, that's why. Okay. So that's very quick, actually. It's already trained for every number of k. So we actually just trained it 100 or 99 times, and we can look at the train scores here. This isn't so easy to read, but the way that we can think about this is that for k of 1, we have 94% accuracy on the training set. K of 2, we have 85. K of 3, we have 86. K of 5, we have 83, and so on. We could, say for IDX, score and enumerate, start at 1, and can print the IDX and the score. And we can see with a K of 1, we can just look at this, and that's fine. We don't care as much, like I said, we don't care as much about the training scores. We care a lot more about the test scores. So let's make sure that that is working. And notice these start off lower and then they get higher. And we can probably, the thing that we want to start thinking about is there's going to be some value of k that's going to be the max, right? And offhand, that looks like maybe it's or some accuracy that's our max. And offhand, it looks like that's with a k of 12. Keep in mind, this is relative to the random state that we defined. And if we change the random state, we're probably going to get a different max. So now we can plot these results. That's a very common thing we would do. So why don't I do that? So let's plot results. And I'm just going to do this really quick and dirty. So patches. This is just to help me build a key. I'm going to get the max score out of CV test scores, right? Because that should be the value that the value of k that we care about the most. Okay, and I am going to start looking through the CV test scores from the other end, and there's a reason for this. It turns out that a lower value of k is more likely to overfit the data. By overfit, I mean it's likely to be too variable, right? It's going to have high variance, sort of like when we connected the dots with a linear model. And with a higher value of k, it tends to be more general, right? You take more votes, that tends to be a more general response. There's a certain point where that becomes too general, right? Where it's highly opinionated, and its opinion is that the majority class is obviously what everything is. That would be high bias, and that would be what we could call underfit. So I'm going to start from the back. I'm going to err on the side of the highest value of k that outperforms other values of k in terms of accuracy. So I'm going to get that, and then the optimal, this is the second part of that. This is just our optimal k is going to be, from our neighbors, it's going to be that test max. That's just our index of the optimal value of k. So let's do, I'm going to set some limits to x and y here, and you'll see what that looks like in a second. It's going to be from the minimum of the CV test scores minus 0.2 and up to 1.1. So why 1.1? Well, we're not going to have a test score, an accuracy score over 1, right? It's, how many out of how many correct out of how many. So that will always be less than 1. I'm just constraining that. And then I can set a y limit. And our y limit is going to be the min from, this is actually our y limit. And I'll make an x limit, which is going to be from 0. This is much simpler. 0 to the length of the number of neighbors that we're looking for, that we're analyzing. So those are the bounds of our plot. And then I'm going to define some patches for our key. So mpatches.patch. I'm going to make one that's orange. That's the name. And that's going to indicate our training. And then I'm going to make one that's blue, which will indicate our test. And then I just set up this legend, right? So plt legend handles. Handles are just the couple boxes that are in there. We have an orange patch. We have a blue patch. And then I'm going to set a title. And I'm just building this string outside, and I'm going to plot the title in a second. So the accuracy of cross-val. And then I'm going to say that we have this optimal k. And now I'm going to plot everything. So axes.plot. I'm going to plot our neighbors against the CV test scores with the label test scores, and neighbors against CV train scores with the label train scores. Okay. And then oh, there's probably something wrong in there, but I also need to set the title. So plt.title, and I'll just pass in the title. Okay, so set ylim. Oh. Am I missing? Oh, I see what's going on there. Ah, there we go. Because I need to get the min. It's not min. This is a list. I can't subtract from a list. I'm getting the min from the list and subtracting 0.2. I just okay, almost there. Awesome. All right, so now we've got something that we can talk about. The optimal number of neighbors from which we're taking a vote is going to be 12. And we can see this in our plot. We've got a peak, right? We've got a peak right there. So we can see that it's doing that. Our test set is doing pretty well when we get to that point. But then we have it kind of starts failing as we go forward. Our training set does really well right here. That's interesting, where we only have one neighbor, and then it starts doing pretty poorly as we add neighbors, as it generalizes. So these don't have to work at odds with each other necessarily. There's a point where they seem to be doing reasonably the same, but we care about the test results primarily. We don't care as much about the train results, but we can describe certain things that are happening here, right? Like over here, we're likely overfit, which means that we're following the data too closely. We are, it's going to be variant depending on the values in the data. And over here, we are underfit, which just means that our model is highly opinionated. Our trained model is highly opinionated, and it's not actually going to do well on either the train or the test. And really quick, let me just show you what happens if we change our random state. Let's change it to. I think I know what it's going to do with a random state of 42, and that's why I want to do that. So let's see. So look, now our optimal is at 45. That's a little surprising. Our optimal is somewhere in there, and I think it turns out that this 42 is a little bit anomalous. Right? Because if I change that random state again, now we're back below, below 20. And if I change it to, change it to random state of 3, and we're still sort of in this region over here. So why is it that, why is the random state making such big differences here? A big part of that is we only have 150 rows of data, right? And so our performance is pretty heavily based on that data. And what we would likely want to do is just run this a bunch of times. What I would do offhand, I would say run this, let's say 1,000 times with different random states, maybe random states 1 through 1,000, I don't know, or with no random state at all, and choose the, with no specific random state set, and then choose the modal value of k. So that's something we could do to find the most optimal value of k in general, right? And we could go forward with that. So there's just a couple short steps here. So let's say we fit our final model. And we do this using the optimal hyperparameters. And this is what we send off for production in general. Although, if you are the person trying to figure out the optimal model, fit model, you might not actually you might not even engage with this part 4. You might hand all those specs off to a data engineer or to somebody else, and they might build it because they might be adapting it to a different space. Like you may have done this in sklearn, and they might take it to Apache Spark and put it across a cluster instead or something like that. But either way, you decide on these optimal hyperparameters. So just one last time, I'm going to build KNN and kneighbors classifier, and I'm going to pass in for the number of neighbors that optimal k, and I'm going to fit the model. So knn.fit, and I'm going to fit on xtrain and ytrain. At this point, maybe I would even spin back in our full data set, so the full data set of x. But that's not generally a good practice or a practice that people would perform. So let's just look at what we get when we, let's look at the, it's just called KNN. Let's just look at KNN and notice we've got a lot of things in here, right? We've got a lot of fields that we can look at. Like we could look at knn.weights. Okay, uniform. We could look at knn.getParams. And these are the parameters. And notice our metric here isn't exactly Euclidean distance. It's not exactly not Euclidean distance. It's Minkowski distance, which is a generalization of Euclidean distance. So we don't have to really think about that too hard. But from there, we just get our final metrics out of this. So let's do model predict. And this is where we pass in our holdout set, which is just x test in this case. So we get x train predict gets knn.predict x train and y test predict gets knn.predict off of x test. We've already done all this before, but this is kind of how you wrap up you're reporting on these things. So report the final metrics. And in this case, we're just thinking about accuracy. So I'm going to print the f string of test accuracy. And this is going to be the accuracy score for y test and y test predict. And I'm going to round all of this to 3 places. So that's what we get. We have an accuracy of 0.9. So that's if we just scan back through this, notice that even in this like sort of simple kind of approach, we have the most time, the most code dedicated to exploring the data, right? Definitely the most area in this notebook. And that getting to know your data is probably the deepest part of what you will do, right? And I think I said this before, you get to know data better than the people who are creating that data in a lot of cases. And you gain this familiarity that you wouldn't get otherwise. And the train test split, searching for hyperparameters, stages of this also teach you a lot about what's happening in the data. Often you're looking for different models, right? You're not just looking for the best way to do KNN. You're looking to see, which should you use, KNN or logistic regression or a decision tree or a random forest or a neural net or, what kind of neural net. And some of these models will work well with some kinds of data and they won't work well with other kinds of data. That's something referred to as the no free lunch theorem. And that's basically saying that there isn't a single model that's going to do it for you. You have to, choose models appropriate for the data and figure out how to tune them appropriately for that data. So, with that, let's take just 5 minutes, and when we get back, we'll start like inventing an interview. Okay, and we'll see how that goes. All right, I'll see y'all back here in a few minutes. All right, so let's get back into this. We're going to talk about the technical interview. And as you all know, we call this the TI. Let's kind of break this down into a few parts. It's 45 minutes. So we, have a timer, and we have pretty much a hard stop at the end of 45 minutes. There's a start time and an end time. And really what you are going to be doing is writing Python that explores statistical or probability concepts. So let's think about what that might entail. So you might need to recognize and solve problems related to binomial, Poisson, geometric, uniform. At this time, we don't have Bayes' theorem in our interview, but depending on when you interview, right, if you're going to interview a month from now, it may be there, right? If you're not aiming for the May cohort, we may have something that's centered much more around Bayes' theorem than what we have right now. But we're going to try to make that an easy thing. An easy transition. And if you haven't interviewed at all yet, there would be 2 interviews before you even got to a Bayes' theorem problem. So that you would have to not pass in order to get to a Bayes' theorem problem. And we might restructure those things later, but currently mostly it's those discrete distributions and then a uniform distribution. So let's think about this problem. This is the just a sort of example, like what you might need to be able to do, understanding sampling approaches, right? So that could include understanding counting in binary, or thinking about binary through the lens of independent trials. Where I think we talked about this quite a lot. We can think of that as being tails, heads, heads, tails, heads, right? In this case, we've got maybe one of those 3-sided sticks that you can roll that have markers for each side, and we have 0, 1, and 2 as potentially possibilities in trinary. Well, we have an easy way of thinking about this currently, where we say, for I in range 3, and then for j in range 3, for k in range 3, and then we have I, j, k as being all the values in that trinary, 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 1, 0, 1, 2, and so on, until we get to 2, 2, 2. So having a fair understanding of counting is really important. Also, thinking about sampling randomly. For either of those, you could sample. Here, let me actually write that down. Counting and sampling. For either of those problems, right, you could use random.choice to build a list of calls from 0, 1, 2, right, for your base 3 system, or 0, 1 for a binary system. And in terms of coding mathematical functions, let's say the Poisson PMF, or let's say the Poisson CDF, right? If you were to see something like this, this would be, the Poisson CDF given lambda and k. This would be, let's say I starts at 0, goes up to k, inclusive of k, of course. And then we're going to say e to the negative lambda times lambda to the I, because we're thinking of I as being a placeholder for each value of k, all over I factorial. So if we give you something like this, which is fairly simple, we'll tell you what it is, and we'll probably even talk you through it a little bit. We'll say, well, what's happening here is it's going to be the sum of all values from 0 up to k, where I take 0 up to k, and that's what is happening on this side. You're summing all the results of that. But you would be expected to be able to implement that in code. So that's something to keep in mind. And then let's say this is your base function. Then the next things that you would need to do, actually, the next thing you would need to do is be able to pack those things in a dictionary. So you code some sort of function, right? Whether that's for math or some other construct, some other phenomenon. And from there, you need to analyze that through a dictionary. So you analyze via a dictionary. And if we think about this is just going back to that general analytic approach that I described, where we create a generative process, you load those results into a dictionary, and then you interpret or transform that in some way. Analyzing via dictionary, you might need to, you will need to solve what I'm going to call a novel problem. So maybe something you haven't seen before, but that incorporates these other parts. So there's some interpretation that happens here, kind of at the end, like interpreting something new, interpreting this novel thing. That could be recognizing a pattern or describing the application of a statistical concept that maybe you haven't seen before, or that you likely haven't seen before. So why don't we start thinking about an example here? And let's do this in let's just do this in Python, just raw Python. Depending on who gives you the interview, like if it's me, I will likely use REPL to deliver the interview. Other people will connect you to a virtual machine. It just depends on who's giving the interview. But in general, just expect to be in a Jupyter notebook solving these problems, connected to a remote machine. So you would use TeamViewer to log into the remote machine, and then we'd have the notebook up there for you, and you would just use that. I will occasionally use Replit because, I don't need to talk about why, but I kind of like it more for the interview. And then I just share the notebook with you. So let's think about a problem. And the problem that occurred to me before was something related to dependent sampling. So let's kind of invent this. Let's start with a phenomenon that has 3 different potential outcomes. So let's say it's going to be random. So I'm going to say from random, import random. And with that, maybe I'll make this a little bit bigger. With that, we can define a function. So let's say get let's get a result. How about that? And let's set a yeah, let's think about this. Let's just get a result. I just thought of a way to make this much more complex, but let's keep it simple. If So let's get a random value out of random. And remember, random is going to give us a value between 0 and 1. So let's just get rand gets random. If rand is less than, I'm just going to say 0.33, then return 0. Elif rand is less than 0.66, return 1. Else return 2. So can you think of another way we might write this? Something that might be a little simpler. We could rewrite this using random choice. Right? I could just say random choice between 0, 1, or 2. And that would be essentially equivalent to this, maybe I should put more 3s there, but let's just say that this is what we're working with. We could adapt this function to be a little bit different. So how about we say prior result, and prior result is going to start off at 0. And let's say random result, or this 0.33, actually this will just be 0. And let's say 0.33 minus prior result times 0.001. And let's take that same thing and maybe we'll change that to a plus. So now we have this thing that's doing something, right? Like, what is this doing? If we think about the prior result, by default that's going to be 0, but we could think about this as, okay, if the prior result is 0, then 0.33 minus the prior result times 0.001, well, that's going to decrease this value of 0.33. And maybe that's not enough, actually. Why don't we do that? So if we get 2, then this is going to go down to 0.13. And let's change that to 0.1 as well. Okay, so remember with binomial, right? With binomial, we have a series of Bernoulli trials. And those Bernoulli trials are independent of each other. But now one trial affects the next trial. And that's what we're going to try to do. So let's get def get n trials. And actually, let's just call that get trials. And let's set n to 12. And let's think of how to do this. So the first thing we're going to do is say we have some list, and it's going to, let's initialize it with a single trial. So we'll start there. And then we don't need that, but we'll need it in a second. And then we can say for whatever in range n minus 1, right? Because we don't need all 12. We've already got one of them. So we can say n minus 1. Then we can say list.append, get result. And we need to have the prior result here. So maybe we want to keep this index Or, just to make this a little clearer, why don't we do this? Why don't we say res gets this, and then we'll put res into there, and res gets we'll say res2 gets, trying to think of the easiest way to make this obvious. So we're going to pass in res, and then we'll just do this. Res gets get result of res. So we're overwriting res at that point, and then we're appending it to the list. So let's see how that works. So how about we return that list, and let's see what this works out to. Prior result is not defined. Prior res. Okay, so we don't really know what this distribution looks like at this point, okay? And I think that's important. That's an important thing to consider. So I'm going to paste this code in. And without coding anything, how can we get a view on this distribution? How could we start going about doing that? Yeah, we can plot it as a histogram. Plot on the count, sure. Yeah, and we want to start thinking about, well, we've got these lists, but what are we getting out of these lists? This is a series of trials, and how do we want to use these? How do we want to use these? Yeah, and we can pack this into a dictionary. So let's think about this from a couple different angles. Maybe we could just say the result of this phenomenon is the sum of these values. We could do that, right? That's something that would be fine to do. Now, is that what we're going to do? I'm not sure. But, if we're just dealing with this list, then, and we're trying to analyze it, maybe this equates to a tuple where, we've got count of, let's say we put this into a list, and we have zeros gets list.count of zeros, and ones gets list of count of ones, and twos gets list of count of twos, and then maybe we have a tuple. So our tuple would be something like zeros, ones, twos. So this would get us a single tuple, and then maybe we're going to sample from this phenomenon a bunch of times to get these tuples. But I want to do something a little bit more obfuscating of the underlying process. And so what I'm going to suggest is something a little different from that. We're getting this list. Why don't we do something like this? Let's do 1 over n times the sum of, well, let's do I equals n down to well, let's not do I equals n. Let's do I equals 0 up to, let's just call it j. And, sorry, let's call it n. And for this, let's do 1/3 times each value in that list, which we'll call x sub I. So 1/3 times x sub I. Well, why don't we just leave it at that? How about that? So let's define this function as call it process list for lack of a better word, and let's set by default n to be 12, and I'm going to put 4 minutes onto a timer. Go ahead and write this function really quick. So let me just remind you, there's the get trials function that you're going to need. Oh, yeah, you can see it there. So you're going to call on get trials. Okay, so 4 minutes. See how it goes writing that function. So this is probably tricky to think about, partially because it's in this mathematical language, right? But all we're going to do here is we're going to call and get a list from this get trials, right? So this is our list. Maybe I'll say this is our big X, right? So I'm going to get trials of n. And then if we break this down, whenever you see this summation, that should stick out to you like accumulator, right? And with that, we can think of just building an accumulator. So just call it accumulator. And I'm going to set it as a float just because, you know, it looks like it's going to be float valued. And then for each value, so for value in, well, I'll call this x, little x in big X, we can say this is going to be 1 over 3 multiplied by little x, right? And from this, we can just collect these into the accumulator and return the accumulator divided by n. So I kind of broke this into a couple parts, right? I dealt with, in the loop, I deal with each of these this 1/3 multiplied by each value of x. And then I'm summing for each value of x, right? So that's in this outer, the shell of the loop. And then at the end, I'm just dividing by n. So kind of getting used to this form of mathematical language. We're not going to ask you anything, you know, particularly more complex than something like that. Yeah, this is us processing a list to get something out of it. So let's see what we get on a random call to process list. So print process list, and let's see what that looks like. We get function because I didn't actually call the function. And we're calling that with a n of 12. So 0.25, 0.33, 0.36, 0.27, 0.33, 0.416, 0.416. Now, this strikes me as having not that many different values resulting, actually. And I think that's interesting. I didn't know that beforehand. But this is kind of the thing about inventing some process on the spot. So, you know, if we look at this a number of times, and maybe what I'll do is, let's say for whatever in range, and we'll just do 100. Let's print process list, and then I'm just going to call for input. And that'll let us look at this over and over again. So 0.333, 0.333, 0.361, 0.388. This looks like we're always getting that there's only a limited number of values we might get as a result. And it's likely that some of these values will be more common than others. So what we could probably do is think about this. You know, we could probably start off by saying, well, what if we have an n of 1, right? If we're going to think about this phenomenon in some way. Well, what if we have an n of 1? Well, it looks like we only have 3 potential values. What if we have an n of 2? Right? And this is just me analyzing the phenomenon. This isn't, you know, so now how many different values do we have? Well, I'm not sure. I'm not sure offhand, but it looks like it's, you know, at least 1, 2, 3, 4, 5 values. Okay. Now, let's say we want to fix this at n is 12. We could go about analyzing this in a couple different ways. One way might be to try to figure out for various values of n how many different unique values we're gonna get. So that's one approach we could take. And let's make this a choose your own adventure. We could either take that approach, or we could take the approach of, with a fixed value of n, like let's say n is 12, what is the distribution of the values in n? So which would you vote for? We either discover variation between, we either discover the number of unique values for each value of n, right, starting at n is 1, going up to say n is 12, or we, which is option 1, and then option 2 is we fix n at 12. So which do you all want to do? I think 2 is a little bit easier, and a little more easily insightful. And you know, it's analyzing a distribution, so that looks pretty familiar. Although we might have time to do a little bit of both, but let's do option 2. So the way that I'm going to approach this offhand is through sampling. You know, so I'm gonna write a function called sample process. And let's set num samples to 1000. And with that, I'm going to make a dictionary, right? And we're going to collect everything into the dictionary. This is going to look just like what we did in discrete distributions, right? It's going to be very much the same as what we saw throughout that. And I'm going to say for whatever in range num samples, we're going to get a list out of process list. And I'm going to build a simple counter, a simple counting dictionary. So how this will look is if, oh, this isn't a list, I'm sorry. This is a result. Let's call it a result. If result is not in the dictionary, is not in D. So we might want to round these, right? Because we've got all of this going off to the right. That's going to be a huge dictionary key, and these seem pretty consistent past a few decimal places. So, well, you know what? I don't want to say that too soon. Let's go ahead and just do this. We'll say d sub res. We'll initialize that to 1, or we'll increment it by 1. This is not usually the format I do this in, but I'll just do it here. Okay. And then we can return that dictionary. So I can say for k, v in sample process. Actually, why don't we just get a dictionary out of that and say d.items. Now, I'm going to use sorted here, right? Because it's a sampling process, and I don't know. It might be easier to look at these if they're in order. So that's how I'm going to do that. So I'll say k and v. I'm probably going to want to round this k value, but let's just see what we get. Okay, so I think this is pretty interesting. I think there's a call we probably want to make on this, right? We've got these 3 different occurrences of, let's say, 2.777, etc. Why do you think we might have 3 different ways of calculating multiple different ways of calculating 0.277, all of this? Because My suspicion is that these are basically the same number. Why do you think that might be? Any thoughts? And it may not be totally obvious here, but there's going to be some list that gets us this kind of value. And given how we calculated this, right, we've got this 1/3 multiplied by x sub I, it might not actually matter where these numbers are, whether it's 0, 1, 2, where the 0, 1, 2 ends up. So these are probably 3 different results for 3 different orderings. And then what we're seeing on the end of this over here is some kind of rounding error just because of how a float is stored in memory. So with that, we should probably round these, and let's round them. Let's figure out what makes sense for rounding. Let's round these to let's just round them to 4 or 5. Let's round them to 5, and that should be safe. So why don't we do this? We'll say if let's round it here, actually. Round 5 places. And I think this is going to help us look at this distribution in some more clear way. So we've got enough here that we can start describing this, actually. And this is really the point. We don't really understand the phenomenon deeply that we created, but we can look at it. And that's really a starting place. So we can see that we have in this scheme a minimum value of 0.08333 and a maximum value of 0.5. And given our scheme, why I don't know why. I don't know why we have this maximum value of 0.5, but we do. And notice this other breakdown, right? Notice these counts, because I think that's interesting as well. 1, 7, 6, 17, 55, 60, 110, 147, 158, 162. And it looks like somewhere in here, like one of these two values is going to be kind of a modal value. Our expectation is probably somewhere right in there. Maybe it's even out of these 3. It's not entirely clear. We could dig into this phenomenon further, and this is kind of the point, is that we could seek to understand this and why we're getting these outcomes. Any ideas on how we might seek understanding what's happening here? Yeah, we could look at measures of centrality, I think. It's a little bit, right, we could take, we could plot a histogram of this, right? But that's essentially what we're seeing here. Our expectation, we might consider to be, say this value multiplied by 158 plus this value multiplied by 162 plus this value multiplied by, etc., divided by the number of samples. And that'll give us something akin to the mean, something that is mean enough for us. The 5-number summary might be interesting here, actually. Might give us a sense of distance from our central place. Yeah, I mean, the way that I was thinking about calculating an expectation here is that this value times 1 plus this value times 7 plus this value times 6. We could go through that and discover an expectation, much more clearly. But remember, this is a sampling process, and as such, we're going to probably want to collect a number of different expectations and take the mean of those. But either way. So here's what I'm thinking, and this may not be the obvious first thing anybody's thinking of, but what if we returned the accumulator and we also returned x here, okay, in this process? And when we get down here, this result is actually going to be the result and that value of x. And we could say, instead of counting, what we could say here is this dictionary is going to be initialized as a list, and maybe I'll just modify this a little bit and say let's append the result. So append the x value. That's what I mean to say. We'll need to append we need to take that result and round it to 5 places, just to be, so round result to 5 places, and we'll just overwrite it, and that'll just keep that a little cleaner. So what we're going to do now is get a bunch of lists in light of each result. And what we could even do is look at all the different, how do I say this? Look at the different ways, the unique ways that we can get the same result, okay? I think this might be telling. So maybe instead of this, I'm going to do a nested list. Well, let's think about this. This will be 1 comma that, and then d res sub 2. No, sub 1. Okay, yeah, that's what I'll do. So I'll have a nested list here, and here's my counter. Actually, let me start that at 0. And d res sub 1 dot append the list is something that we'll do if x is not in d res sub 1. Okay. And under every condition, d res sub 0 is, d res sub 0, we're going to increment by 1, okay? So that might seem a little obtuse, but all I'm doing is creating a counter and a list of lists associated with each individual key. And then in this case, for key value in sorted d dot items, let's look at the key and v sub 0. And then for list in v sub 1, let's print that list. Let's see if that works. There's a good chance that there's something a little off in there, but let's find out. Okay, so that actually seems like it is working. And let's add some space here, just to kind of make this a little nicer. And see what we get. Okay. So are these all unique? Well, it kind of looks that way. Does it matter if these are all rearrangements of the same numbers? And I think that's the next question we might want to ask, right? This value seems to have a higher occurrence than, say, these values. But these are all the unique permutations. Not all. This is not exhaustive. This is likely not exhaustive. But we're getting some number of unique permutations. Actually, in this case, we're getting 1, 2, 3, 4, 5, 6, 7, 8. So here are 8 of the permutations that might lead to 0.5. But do permutations matter here? Think about that. Do we need permutations? Yeah. Given the way that we calculated this, we don't actually need permutations. The order of these results doesn't matter, so we could take this a step further. We could say if the sorted version of x is not in dres, then let's append the sorted version of x. And that should trim this down a little bit. Okay. So it looks like there are two different combinations that will lead to 0.5. And I think this gets us a little closer to understanding maybe why certain values are coming up more, right? There's so far there's 2 combinations that lead to 0.4722. There's 3 that lead to 0.4 all fours. There's 4 that lead to 0.41667, which I'm sure that's just 6s repeating. There's 5. I mean, this is kind of interesting. There's 5. There's 4, although, maybe we just need to take more samples. And let's try this with, 100,000. See if that takes too long. Nope. Oh, wait a minute. Oh. No, that worked. Okay. So notice this. The more combinations that we have, the more prominent certain values are. And that kind of makes sense, right? That, the more ways you can arrange something, the more likely through some random process that result is going to happen. But then there's probably something else going on under here, because if there are 5, oh no, that's 6, and that's 5 arrangements, or sorry, 5 combinations, and this has, I think we discovered something, right? There are 7 combinations here, and this value is seems to be more prominent than the related values. This seems to be the most prominent value here. And there are more combinations that lead to that outcome. And I think that should be telling, right? That should be like, oh, wow, who knew, right? But it kind of makes sense when you break it down that way. There are more ways to get to that same answer. And so through the sampling process, that's what we're seeing. Remember, though, that in the original sampling process, and this is a minor point, but remember that we have dependent sampling. So even though the permutation does make a slight difference, it seems to not make enough of a difference for it to affect these general outcomes, right? It doesn't make quite enough of a difference to really sway this, and we do get a more prevalent outcome here. So don't worry. Don't worry. The TI is easier than this, but it's the same skills. Okay. This is an obtuse statistical concept that I kind of just made up on the spot, and then we were able to discover something from it. But this emergent property of like, well, if there are more combinations that lead to a specific outcome, then that outcome is more likely to occur, in the underlying framework. There's a little bit of extra information here, right, with this dependent sampling process that didn't make a whole lot of difference, right, in this outcome, but that's fine, right? It made some difference that we were able to see in the variable, like in the variations of each of these buckets, but it didn't travel too far or below that bucket. And we could, if we really wanted to, we could analyze the number of we could analyze the number of these different permutations. These are combinations, but we could go back to permutations and we could look at all the different ways that all the different numbers that those permutations have that sort of cluster, all the different numbers that those permutations result in when we process them, and what those look like in their cluster around this bucket value that we have here. We could do all of that, and we could understand this invented thing pretty deeply if we want. It turns out that there are a lot of things that are more helpful to spend time trying to understand, but you have a tool set in front of you, even with just the basic Python, just core Python that and this analytic approach that you could analyze all kinds of statistical concepts, all kinds of mathematical concepts. You can invent mathematical concepts and explore them, and that's really, really what this is about, and that's what we want you to be able to demonstrate a little bit in the interview, right? Although that's mostly going to be, it'll be a simpler phenomenon than this, let's say. Though, I might adapt something like this because I really like dependent sampling as a thing, and so if you if you don't pass your interview twice and you get to a third interview and there's dependent sampling on it, don't be surprised. Thanks so much for everything, for being in class, for participating, and spending these the last 5 weeks. Don't hesitate to reach out. Although I'm going to be sort of sequestered. I have a conference. Sorry, let me stop recording.